In the previous lecture, we had seen how quantum Fourier transform can be used to find out the period of a function. Actually, what we did was to show that if you assume a given period, then there would be only certain states which would be appearing in your first register. In particular, what we found is, for the case of 3 qubits, if you assume a function with a period of 2, the measurement of the first register will either give you a state 0 or give you a state 4. Similarly, if you had assumed a different period, then one can easily work out what would have been the content of the first register. It's not a unique, but on the other hand, depending upon your value, the periodicity of the function, you can find out what are the possible results of measurement of the first register. So therefore, if in this example that we gave you, if the first register gives you a 0 or a 4, one can conclude that the periodicity of the function is 2. So periodicity determines the non-vanishing states in the first register. Now, this is an important information that we will be utilizing later on. The next question that we want to ask is, so we have seen that if we can take a Fourier transform, this is what will happen for a periodic function. The natural question is there a unitary transformation which actually will do this job? So let me sort of explain what do I mean by this. So I had an arbitrary state psi in the computational basis, sum over x, ax, x, and we said that my psi prime is operator u acting on psi, which gives me by linearity sum over x, ax, ux, and that's equal to sum over y of ay tilde y, where your ay tilde is 1 over square root of n sum over x omega to the power xy x, where omega nth root of unity, and as a result my u has a structure which is sum over yz e to the power 2 pi I yz over n by square root of n, and you have a y to z. You can see that this u acting on this here will, because z must be then equal to x, so therefore you will get the right factor that you want there. So this is the type of operator that we are looking for. So once I have got a structure of x, which is here, now notice one thing, it tells me that if I started with a standard basis, so what happens if I let u act on my standard basis? So I will get x tilde, which is my new basis, is uf acting on, let us say one of the basis states is x. So this will be equal to 1 over square root of n sum over y equal to 0 to n minus 1 e to the power 2 pi I xy y. Now this is also a linear combination of the basis states, but unlike the Hadamard transform, this is not the coefficients here are not equal and they are not unity, and in fact they are complex. But these are all unimodular because e to the power 2 pi I xy has a unimodular, the value of modulus is equal to 1. Now, let me look at how does one implement the QFT. The simplest way of doing it would be to look at systematically what happens for the single qubit case, for the 2 qubit case, and then the generalization will be obvious. So, let me take a single qubit case, n is equal to 1 corresponding to capital N is equal to 2. Now, what is x tilde? So, x tilde is 1 over square root of 2, sum over y is equal to 0 to 1, e to the power 2 pi I xy divided by 2 of y, there is n missing there. So, since y takes values 0 and 1, this is 1 over square root of 2, 0, the coefficient becomes equal to 1, e to the power 2 pi I, now y is equal to 1, so I am left with an x, so I get x divided by 2, 1. Now, I am going to write it in a slightly different notation, and the notation is this, that if you recall, since my x, y, etc. in this case, this way of writing takes values 0 and 1, the x by 2, this binary expansion is simply 0.x. Let me explain what I mean by this. See, in a typical decimal number, when you write for example 0.4, what do you mean? When you write 0.4, it means 4 by 10. If you write 0.03, it means 3 by 10 square, that is 3 by 100. In this case, my basis is 2. So, therefore, if I write something divided by 2, the binary point or binary decimal is a bit of an oxymoron statement, but binary point representation is 0.x. So, I will write this as 1 over square root of 2, 0 plus e to the power 2 pi I times, instead of writing x by 2, I will write it as 0.x1. Now, what is this? Now, notice this is nothing but a normal Hadamard transform. Why? Because if this x happens to be 0, so that I got e to the power 0 equal to 1, I get 0 plus 1 by root 2. On the other hand, if this x happens to be equal to 1, now remember 0.1 in binary point representation is 1 by 2, so that I get e to the power 2 pi I by 2, which is e to the power pi I, which is equal to minus 1. So, I get 0 minus 1 by root 2, which is as it ought to be in case of a Hadamard gate. Now, this is of course trivial. So, therefore, in this particular case, the QFT for n is equal to 2 is implemented just by having a Hadamard gate. Now that we have seen that for n is equal to 1, that is capital N is equal to 2, the Fourier transform may be implemented by application of a normal Hadamard transform. We will continue, and let me take 2 qubit case, n is equal to 2, so that capital N is equal to 4. Now, let me write down the Fourier transform. So, this is 1 over square root of n square, because there are 2 of them, y is equal to 0 to 3, e to the power 2 pi I x y by 4, and y of course. Now, remember that in this way of writing, x and y are 2 qubit situation. So, therefore, let me expand this by writing y is equal to 2 y1 plus y0. I will for the moment keep x the same, where y1 as well as y0 they take value 0 and 1, and my state y I will write as y1 y0 is a direct product essentially. So, let me write this as equal to 1 over 2 sum over y1 and y0, keeping x the way it is, 2 y1 plus y0 by 4 and y1 y0. Let me break up this term into product of 2 and distribute this 1 over 2 into 1 over square root of 2. So, the first term I will write it as sum over y1 e to the power 2 pi I x into 2 y1 divided by 4 and y1, product with sum over y0 equal to 0 1, here also it is 0 1, e to the power 2 pi I x, and you have y0 divided by 4. And there is a 1 over square root of 2 which is coming along with this. So, let me, since I do not have space there, let me put it like this. Now, we are going to see what are these terms like. Realizing that my y1 takes value 0 and 1, let me first split it up. So, I have 1 over square root of 2, 0, because if y1 is equal to 0, this e to the power 0 is equal to 1, plus e to the power 2 pi I x by 2, because this is 2 by 4 and y1 is equal to 1. So, I have got 1 here and multiplied with 1 over square root of 2, first term is 0 as before, plus e to the power 2 pi I x, y0 is equal to 1. So, it is x by 4 1. So, this is what I get as the Fourier transform of the 2 qubit situation. Let me now expand this x and realize that x is equal to 2x1 plus x0. Now, if that happens, if you look at this term here, I have got 2 pi I x by 2. So, e to the power 2 pi I x by 2, x is 2x1 plus x0 by 2, and that is equal to e to the power 2 pi I, this 2 by 2. So, it is x1 multiplied by e to the power 2 pi I x0 by 2. So, notice one thing, for both x1 equal to 0 as well as 1, this term becomes equal to 1, because e to the power 0 equal to 1 and e to the power 2 pi I is also equal to 1. So, therefore, this term that I had written down here can be rewritten as 1 over square root of 2 0 plus e to the power 2 pi I x0 by 2. This is coming from here, because this is 1 times vector 1 multiplied with 1 over square root of 2, again 0 plus, but this time I have 2 pi I x by 4. So, let me write it as e to the power 2 pi I, and x is 2x1 plus x0 by 4 1. I do not change the first term, let it keep the way it was, e to the power 2 pi I x0 by 2 1 multiplied by 1 over square root of 2. Let us look at this term, this is 0 plus. Now, look at this term here, it is e to the power 2 pi I into 2x1 divided by 4, which is nothing but e to the power pi I x1.
So, e to the power pi I being equal to minus 1. So, this term is minus 1 to the power x1, and the phase term is still there, which is e to the power 2 pi I x0 divided by 4. Now, we need to rewrite these in a particular way. I had already told you that this thing, which is x0 by 2. Now, since it is a single qubit, x0 by 2 can be written as 0.x0 in the binary point representation. And let us look at what do I get here. Here I have got e to the power 2 pi I x0 by 4, and here there was a minus 1 to the power x1, which I had actually written from here. So, let me bring back the phase notation. So, it is 2 pi I. So, x1 is what I had. So, this is equal to e to the power 0. See, here I have an x1 and I have here an x0 by 4. So, this is 0.x1 x0. Sorry, here there should have been a 2, because this is 2 x1 by 4. x1 by 2 is 0.x1, x0 by 4 is 0.0 x0. So, finally, if I collect them all together, I am getting 0 plus e to the power 2 pi I 0.x0 1 over square root of 2 0 plus e to the power 2 pi I 0.x1 x0 1. The thing that I want to point out is the following, that these terms, actually this term is not particularly important, because here I get minus 1 to the power x0, so which is nothing but an ordinary Hadamard transform. But supposing I transform the first qubits Hadamard, then this term, where there is a phase rotation, depending upon what the value of x0 is, then I will have a problem. And because of that, I need to change. You notice here we have got e to the power 2 pi I 0.x1, which is nothing but minus 1 to the power x1. This is what you expect of an ordinary Hadamard transform. But the phase factor is e to the power 2 pi I x0 by 4, and that phase is there only when x0 is equal to 1. But if I had changed the value of x0 here, instead of keeping the old value, then this would mess up things, not the way I want it. So, what is important is to remember that I want certain action to be taken in a particular way, and since I need the x0 to provide a control, I cannot apply the gate on x0 before I have done this, and that is the reason why we will see in the slide that our circuit requires a reversal of x0 and x1 before the various gates are given. Now, how does one implement such a thing? The way to implement this is this: we define what is known as a controlled BJK gate. I define the matrix BJK by the following: 1 0 0 e to the power 2 pi I divided by 2 to the power k minus j plus 1
The reason why k, j, etc. occurred here, we will see when we extend our logic for n is equal to 1 and n is equal to 2 to the general case. But this is what a controlled BJK gate does. So let us look at what is the effect of controlled BJK on, let us say, state xy. The controlled BJK gate acting on this gives me e to the power I, okay, let me write it, 2 pi I by 2 to the power k minus j plus 1 xy, that is a phase factor xy. Now what does it give me? It tells me if x is equal to 0, this is nothing but xy. On the other hand, if x is equal to 1, it picks up a phase, that is exponential of 2 pi I by 2 to the power k minus j plus 1 y. Now with this, let us return back to our previous slide. So we said my x tilde, which was the Fourier transform, was given by this slide. So x tilde then becomes equal to, first one as we said is just Hadamard, 1 by 2, 0 plus minus 1 to the power x 0 1, nothing to be done there. The second one, if you refer to the slide again, it was this term here, 0 plus e to the power 2 pi I 0.x1 x0, which we had seen can be written like this. But you see, this is the controlled phase rotation. So what we will say is this is equal to B12 0. Why 1 2? Because I had defined BJK gate as given by this. So if j is equal to 1, k is equal to 2, I get 2 minus 1 plus 1, so it is 2 square there, e to the power 2 pi I by 2 square. Now this is precisely what we had here in the slide. So that this thing we should be able to write as B120 acting on 0 plus minus 1 to the power x1 on 1. So these states are entangled because you notice the first one, which refers to x1, has a minus 1 to the power x0 there. But the second one has minus 1 to the power x1 there. So in other words, the output is in reverse order. Now, so what do I do? The way to mend this situation is to do the following. X tilde is half. The first term is UH x0. Second one is B12 0. UH acting on x1, which is equal to half of UH cross I B120 I cross UH, the different order because one of them acts on the x0, the other one acts on y, but it acts on x0 x1. This is what we want. But you realize that what we had was a state which had x1 x0. So therefore, I would write this as 1 to UHI B120 else I swap x1 x0. So what it means is this: before applying these operations, we must swap the order in which x1 and x0 are appearing, and then carry on this thing, so that my final state comes up in the correct order. Because what we noticed is my x1 and x0 were getting swapped. Now look at a picture. So this is what we said here, that there is a rotation, selective rotation, depending upon what is the value of x0 in the second one. And a simple circuit will tell you this, that supposing you had a x1, x0, now you don't want these operations to just take place on x1, x0. So what I do is, I swap these first. We swap it, and then as we have seen that on the first line, which is not affected by this control, I put a Hadamard gate there, and on the second line I put a Hadamard and B12 there. Now if I do that, then the operations would have been done in the order that we want, because the way my states came, they were reversed. So we have done couple of things in this and the previous lecture. One was to point out that quantum Fourier transform can be used to infer the period of a function which is periodic with a discrete periodicity. And the second one we saw by specific examples of 1 and 2 qubit cases, how to implement Fourier transforms in a quantum circuits, and for that we had two additional things, namely a controlled BJK gate and a swapping of the bits before we apply these transforms. We will see later, when we extend this idea to a general n qubit case, what we have to do is to permute the bits first and then apply the operations, the BJK gate, the Hadamard gate, etc.